Okay, so thanks for coming today. I'm Fukami in UCLA. So today let us introduce the use of probabilistic neural network for reduced order modeling for fruit flows, which can be regarded as an example of high-dimensional complex nonlinear systems, right? Good. So as you guys know, the neural networks have shown their great potential as an universal approximator in physical sciences, right? But the thing is, usually these neural networks have been handled as a black box, which means it is relatively tough to get the feedback from the inside the neural networks, right? The one of the reason here is that usually the neural networks are optimized through the L2 error-based minimization manner, which causes a deterministic regression. I mean, there is kind of no notion of confidence interval of its estimation, right? So today, let us focus on the use of this probabilistic view because the recently the variational inference or the Gaussian process approximation have shown their great potential thanks to this probabilistic manner, and this idea also enable us to not only assess the model and but also perform the uncertainty quantification. Right. So today we consider the use of neural network aided by the probabilistic manner called the PNN probabilistic neural network. Good. So in this page, let us briefly introduce what is the probabilistic neural networks, right? So this PNN can focus on the probability distribution of estimation, which can be approximated as a linear superposition of the Gaussian distribution of its estimation, mean value of its estimation mu, and the standard deviation of its estimation sigma x. Okay. So this PNN can attempt to get the probability distribution of output directly. Okay. So to explain that point, let's consider this example illustration. Okay, so in this example, our machine learning model attempts to estimate the global profile of a two-dimensional NaGa 12 wake with a guiding from the local sensor information. And in this case, sensor informations are located on an airfoil surface like this. Okay, so thing is, if you want to perform this idea with the conventional multi-layer perceptron neural network with the L2 error minimization, we can just get the output with the deterministic manner. But in contrast, thanks to the this probabilistic idea, actually in this model, we can also get the sigma x, I mean standard deviation of estimation in addition to the mean value of its estimation like this. Okay, so this standard deviation map or confidence interval map can be utilized for performing the uncertainty quantification like this. Okay, and as a loss function, we also consider the use of the maximization of the log likelihood, which is also distinct against the L2 error minimization. And this idea is also suitable to utilize the full distribution of estimation by PNN. Good. So we apply this idea of the PNN to construct a reduced order modeling with proportional decomposition POD, which is also known as a principal component analysis PCA. Okay, so our strategy here is first we take the POD for flow field data and then obtain the temporal coefficients such as Q equals to Q0 plus summation of AIPA, and this A is exactly the POD coefficient. Okay, then the PNN attempts to predict the temporal evolution of the POD coefficient over n time steps from the local sensor information S at the first time step. Okay, so then now summarizing, the input is the sensor information at the first instantaneous steps, right? Then PNN attempts to predict the temporal evolution of the POD coefficient over n time steps. So, I mean, this problem setting can be regarded as the temporal prediction. Okay, so as the example, first we consider a wake of NaGa 12 airfoil with a guiding flap. Here, the input is the 5 sensors on the surface of an airfoil, then output is the 50 POD modes over 12 time steps. So this first shows the relationship between the estimated coefficient and the magnitude. So as shown here, the estimated coefficient colored by red show reasonable agreement with the solution data illustrated as this gray line, while showing its confidence interval like this blue curve, right? And the beauty here is actually we can also get the high dimension representation, I mean high dimension flow field, by combining with the predetermined POD eigenvector phi. So actually we can also visualize the high dimensional estimated flow field like this. So this is a reference with the 50 POD modes, and this is reconstructed with the estimated coefficient with predetermined POD eigenvector. So as shown here, the flow field show the reasonable agreement with the difference field, and the feature reports approximately 2% errors, right? Actually, we also applied our this PNN idea to the North Sea surface temperature as an example of more practical manner, right? In this case, the input is the study sensors as the first week, like these yellow circles, and the output is the 4 POD modes over 100 weeks. So analogous to the week example, the temporal evolution of the POD coefficient show reasonable agreement with the solution data while showing its confidence interval as this blue curve. Then we can also get the high dimensional representation by combining with the predetermined POD coefficient, the estimated coefficient AI. So as shown here, the reconstruction with the coefficient is in reasonable agreement with the reference temperature data. So summarizing above, now the estimations are well done while showing, this is an important point, that their confidence intervals, right? And this idea can be utilized for performing the uncertainty quantification. And at rest, we also refer to you guys this paper, and our paper also includes the discussion for the data recovery perspective on the fluid flows. Yep, that's it. Thanks for listening.